Hey guys, welcome to the Aeromechanics of Solids class. So this is Professor Nehru, Department of Aerospace Engineering, Essence College of Technology. Today we are going to see the shear flow in open section, and then we are going to see what is the shear flow and what is shear center. So first we need to understand what are the restrictions to be done before solving the problem and finding the shear flow and shear center. The restrictions are shears at every point in the beam must be less than the elastic limit of the material due to the applied shear, right? Second one is the normal stress at every point in the beam must be less than the elastic limit of the material in the tension as well as compression. Third one is the beam's cross section must be contain at least one axis of symmetry. So the axisymmetric material will be considered while solving the shear center and the shear flow. And next, the applied transfer of lateral forces at every point of the beam must passes through the elastic axis of the beam. Recall the elastic axis is a line connecting cross section shear centers of the beam. So it is said that so all the elastic line or the elastic line in the cross section which is connecting the all the shear center of the beam. So next the length of the beam must be much longer than its cross section dimension. So length should be very long comparing to the cross section of the structure. Then finally, the beam's cross section must be uniform throughout the length. So this is the arbitrary material. The length should be the cross section and the length should be uniform. It should not be any deviation. So coming to the shear center, what is my shear center? If the line of action of the force passes through the shear center of the beam section, then the beam will only bend without twist other than the twist will be accompanying the bending. So it means that the shear center is a point where the structure take place only bending without twisting. So this point will understand or this point will express the property that it will takes only the bending of the structure. It will not create any torsion or twisting. The shear center is in fact of centroid of the internal shear force system, depending on the beam's cross section shape along its length. So the location of the shear center may vary from the section to section. Let us take a different cross section. The shear center will be varies based on the length, thickness, and the shape. And a line connecting all the shear center is called as elastic axis. So every cross section we have different cross section and different section. Each section will have different shear center. If you join all the shear center location and you will get an elastic axis. So this line connecting all the shear center is called as elastic axis of this particular beam. So when a beam is under the action of a more general lateral load system, then to be prevent the beam from twisting and the load must be concentrated or centered along the elastic axis of the beam. So this is the example of shear center. We have three different beams and the applied loads are different. In first diagram, the load is applied in the right side, and the second diagram it has in the left side. And third diagram, the load is acting in the mid side. So the cross section representing the beam is bending as well as taking the twisting in the first diagram. Second diagram rotating or bending towards the anti-clock direction and it also bending. Whereas in the third diagram, the beam is the only takes bending without twisting. So this is the point where we will say for that particular cross section is a shear center and the location. The following points are facilitate and demonstration the shear center location. The shear center always falls on cross section of axisymmetric area. For the cross section contain two axisymmetric, then the shear center is located at their intersections of each cross section. So notice that this is the only case where the shear center and center point location coincide. So these are two different examples for the different section. One is the rectangular section or the T section, and the shear stress distribution is represented in the red color, where the neutral axis passes in the intersection, where the maximum shear stress will take place. And the top flange and the web will acting different loads. As a top flange T section, while the load is acting the vertical load, the load is taking by the flange is very low, whereas and the web will take more shear stress. So this is the distribution of two different sections. These are the other different sections and the shear for distribution. I section, the vertical load V takes place, and the web and flange will take top flange and bottom flange is taking a different loads, whereas the web will take a different loads. So it is linear, this is a non-linear, right? So coming to the I section, which is acting in the horizontal vertical load, the web will not take any load, whereas the both top and bottom flanges will take the maximum load as a parabolic curve. Shear for distribution. And coming to the channel section, vertical load and channel section horizontal load, that is where the load flow shear for distribution are represented here. Whereas in T section, the load is acting in vertical direction, both the top and bottom flanges taking the both shear and the bending stress loaders, right? So example, let us take a beam having 100 fixed another load support, and the UDL load is to 22 kilonewton per meter, and the point load acting at the point C 45 kilonewton, and cross section is channel section. So here we have to find the what is the shear center location, what is the shear flow, and what is the bending stress values. So for this we have to find the beam and the load should be determined, and the load location and magnitude of the maximum trans shear force Vmax should be found, and the shear flow Q distribution due to the applied load Vmax, and the coordinates of the shear center should be calculated where this is centroid for the cross section, and the maximum shear stress are located in the cross section. Each location we have to find out. So for that we have to use the formula shear for Q is equal to Ix Vx into Iyxy Vy divided by Ixy Iyy minus Ixy the whole square, and summation of a into x, the location of point where we need to find out the x comma y point location and the area of the cross section, minus Iy Vy minus Ixy by Vx divided by Ix Iy minus Ixy the whole square into summation of y into a. So this represents all the areas and the location of the y location. So this location represents at what location we are going to find the shear flow. So Ixx, Iy, Iyy, Ixy are moment of inertia with respect to x axis, moment of inertia with respect to y axis, moment of inertia with respect to the xy axis. So area and applied load, whether load is applied in the Vx or vertical direction or Vy in a horizontal direction. So different loads will take place here. So this is the thing we will find. So for that problem, the beams and loading should determine, and here we are getting the answers from top angle to the bottom. This is another reference. You can find out the given link. So this cross section is different. This is an angle section, same beam, and but the cross section is different. So here also we can be able to find out the shear center location and shear distribution. So these are the things we have to be have in mind while solving this shear center and excuse me, shear flow. The calculation of centroid, symmetric, moment of area, moment of inertia are based totally on the area and distribution of the beam stiffness. So how much stiffness it has, and web does not change the shear flow between two adjacent stiffness, and as such as would be in the state constant shear flow. The stiffness carries the entire beam into normal stresses, while in the web carries the entire shear flow and corresponding shear stresses. So this is to be a reminder while solving the problem. Right? While doing the analysis, so let being with the simple thin wall stiffened beam, such as a beam carrying only a support of transverse forces that is parallel to a straight line drawn to the center of two stiffener. Example, such a beams are shown in the figure. We have AB, the R is applied, the resistance force, and AB, the collapse has happened, and the AB, the buckling has happened. The D is the radius of gyration. So equal to we have different categories of different points, and the reason the shear flow is equal in the distance between two adjacent stiffeners should be D in all the cases. The applied forces should be in the R in all the cases. The shear flow along the web can be determined by the following relationship, right? So the same the for shear flow equation. The important features of two stiffeners are shear flow between two adjacent stiffeners is constant. The magnitude of resultant shear stress is only function of the straight line between two adjacent stiffeners and is absolutely independent of the web shape. So direction of the resultant shear flow is parallel to the straight line connecting to the adjacent stiffener. So single web beams are the shown here. So here we have this single web. It has the location of the resultants of forces for function of enclosures area. The area is shown in the figure, and shear center location we can able to find, where E is equal to 2A by H is the eccentric location of the particular single cell web. For example, for the multi-web, multi-stages open section beam shown determine the shear flow. Shear flow distribution and the location of the shear centers are shown here. In the diagram, we have different two stages with the curved web, and the answers are shown here. Shear flow distribution and the shear center is located 2.859 distance from the vertical, and the horizontal 0.9813 inches from the vertical. So here we are going to complete this class by getting some questions. Right? We'll see in the next class. Thank you.